double slit experiment. Let me just remind you, and I'm going to close that door now so that we don't hear the extraneous sounds of outside.
Thank you. You're a rebel.
Young's double slit experiment demonstrated a particular attribute of light. Because light would come in like this, these waves would come in like this, and then they would come out like this. Okay? And then if you put a screen here, you end up getting a bright fringe, a bright central bright spot, and then bright fringes symmetrically arranged on either side of that bright spot. Tell me, what was the light doing such that that happened? What's happening here? Yeah, diffraction. Good. And only light waves diffract. That's an attribute of waves. Baseballs don't diffract, but waves diffract. Okay? So another man came along. I think his name was Dalton. I'm embarrassed to say it. Anyone watching this on YouTube, sorry. I remember the guy. But this dude, Dalton, I think, came along and decides, hey, I'm not going to put waves through a couple of slits that get me a interference pattern. I'm going to fire electrons through some crystal lattice. And this crystal lattice essentially is serving like slits. And when you fire electrons through a crystal lattice, just like throwing a bunch of baseballs through a couple of doors, you would expect all these baseballs to hit here and all these baseballs to hit there. So he fired the electrons through the crystal lattice, and you know what happened? Interference fringes, just like Young's experiment. Electrons ended up acting like waves. That is, you threw baseballs through these doorways and ended up with some baseballs hitting down here. And they would all hit down there. I mean, I gotta say again, it was an interference pattern, just like Young got. And so people start thinking, wait, can particles behave like waves? Can waves behave like particles? And that's something called wave-particle duality. In fact, please look at your little sheet. Look at number 1. Young's double slit experiment showing an interference pattern is proof that light behaves like what? Waves. Please put that in there. But when electrons were fired through a crystal lattice, it was discovered that particles also behave like waves. Okay, great. And so, part 3, I'm not going to go into it, but other experiments showed that light exhibits particle-like behavior. So not only do particles act like waves, but light waves act like particles. And so thus you get wave-particle duality. Waves can exhibit particle-like behavior, and particles can exhibit wave-like behavior. And now we're going to start our little journey into waves behaving like particles and particles behaving like waves. Yes?
Can anybody explain why that is, or that's just the way it is?
I'm embarrassed to say it. I don't know. I mean, the real, true reason why, I don't know. I mean, I know all the math, and I know what I'm about to teach you. But why is it that our universe has that happen? I don't know. Yeah. All right. Well, anyway, here we go. Photons and the photoelectric effect. Let me tell you what the photoelectric effect is first. Yay, Tyler's here. Make sure you get it. Yeah. Okay. Photons and the photoelectric effect. First, let me describe the photoelectric effect. Here's the photoelectric effect. You've got a metal. This is a metal surface. And you shine light on this metal surface. Okay? when light hits the metal surface, electrons get dislodged. People experienced it, but nobody could really explain it. Nobody could describe it. They also describe, you're here for the calculus exam.
Yes.
Okay, sorry about this YouTube.